All right, in this video we're talking about intermolecular forces. Again, this is a really important topic if we're talking about melting point, boiling point, solubility. Different things like that are determined by how strong or how weak the intermolecular forces between molecules are. So let's get started. Intermolecular forces are usually represented by IMF. So if you hear IMF, they're talking about intermolecular forces. Intermolecular forces are forces of attraction and repulsion which act between neighboring atoms or molecules. And molecules are just covalent compounds. It's the particle for a covalent compound. Intermolecular forces, IMFs, are weak compared to intramolecular forces. We're going to clarify that in a second. So an intramolecular force is a covalent bond, for example. Okay. That's the forces within which keep the molecule intact in one piece. It keeps them together. Okay. So inter, keep in mind, inter means between. Intra means within. So let's look at the difference in this diagram here. You see the dotted line? We have two different water molecules here, H2O. We have two different H2O molecules. This dotted line is between the H2O molecules. There's some attraction between the molecules, but it is not as strong as the attractions that between the atoms that hold it together as an H2O molecule. This is called an intermolecular force. That's what an IMF is. It's the attraction between molecules. Intramolecular forces, the covalent bonds, are the solid lines. Okay, we've got the same thing over here. You've got a bunch of solid lines, double bonds, and single bonds. But then we've got these dotted lines, which are just indicating that there's some attraction between those molecules. That's called an intermolecular force, IMF. Same thing down here. These are IMFs. And by the way, these pictures come from, I believe they come from a DNA strand. Intermolecular forces are very important in holding DNA together and not allowing it to unravel. So an example here, the covalent bond involving the sharing of electron pairs between atoms is much stronger than the intermolecular forces present between neighboring molecules. So this attraction is not nearly as strong as the covalent bond between an O and H atom in a water molecule. There are three types of IMFs. We are going to talk about them all in a decent amount of detail here. The main thing I want you to know is what their names are and how to tell which IMFs are present. And we'll go through details on that in just a moment. Know that London dispersion forces, also sometimes called dispersion force or induced dipole, we're just going to use LDF most of the time, London dispersion forces or LDF. Those are present between anything with electrons, which is pretty much everything. There are almost no substances that have no electrons in it. In fact, only alpha particles and hydrogen ions are the only things I can really think of that you maybe would see in chemistry class that don't have electrons, and I'll never ask you about that if we're talking about an intermolecular forces problem. Okay, so London dispersion forces exist in every atom and molecule that you're going to be dealing with. They're caused by the distortion of electron clouds, so the substance will be temporarily polar. So it's going to temporarily have a more negative side and a more positive side just because the electrons get shifted over to one side or the other. And the more electrons a substance has, the stronger the LDF. So those atoms that have a lot of electrons down near the bottom of the periodic table are going to have the strongest LDF. The ones that are really small, like hydrogen and helium, are going to have the weakest London dispersion forces. Okay, dipole-dipole forces are present between polar molecules. Those are caused by the attraction between the more negative side and the more positive side of molecules. So I've got the negative side of HCl is really attracted to this positive side, the H side of HCl, of another molecule. So there's a fairly strong attraction between them because there's a dipole and opposites attract. The more polar the molecule, the stronger the dipole-dipole force. So this one is present only in polar molecules. This one's present in everything, including nonpolar molecules. Hydrogen bonds are an extra special case of dipole-dipole force where you have really, really strong polar molecules, or strong polar bonds, like an FH bond, NH bond, and OH bond. Those are the only three. That's why they're underlined. Okay, remember that. FH, NH, and OH. Those are all right next to each other at the top right hand of the periodic table. And they're the strongest, the highest electronegativity, and the smallest molecule, or smallest atoms with such a high electronegativity. That combination causes them to make really, really polar bonds. This is caused by the attraction between an F, O, or N part of one molecule and the H part of another molecule. And that strong attraction, it's just like a dipole-dipole force, but it's even stronger because of how polar these bonds are. So you'll have to remember, FH, NH, and OH bonds are the only ones that can form hydrogen bonds. And remember, it's not a real bond. I mentioned that up here. It's not an intramolecular force. This is an IMF. So we put quotes around it because it's not technically a bond like a covalent bond. We've got some strength comparisons here. One thing that I want you guys to be aware of, especially if you're thinking about taking AP chemistry, is that very often people will say LDFs are the weakest of the intermolecular forces, and that is not necessarily true. LDFs just have a very wide range. They can be very weak, they can be very strong. It depends on how big the atom or molecule is. Dipole-dipole forces have a little bit narrower of a range, and then hydrogen bonds have a narrow range as well. So let's fill in this information up here. Intermolecular forces, IMFs, are weaker than bonds, the intramolecular forces over here, like the ionic bond and the covalent bond. LDF has a wide range of strength. So we can have very weak LDF and very strong LDF. The dipole-dipole force has an intermediate level of strength among the different types of IMF, so it's fairly strong. The H bond has a greater level of strength among the different types of IMFs. Since LDF has such a wide range, LDF can be as strong as hydrogen bonds. Here's the stuff you really need to know. That's information that you're going to come back to if you take AP chemistry. This is what you really need to know how to do. Anything that with electrons has LDF, polar molecules have dipole-dipole and LDF, and molecules containing FH bonds, NH bonds, or OH bonds have hydrogen bond, dipole-dipole, and LDF. So the question here, does the molecule have electrons? Well, yes, of course it does, right? These bonds represent electrons, these lone pairs represent electrons. In fact, we could go down right now and see that all of these have electrons. So we're going to say yes for every one of these. Yes, they have electrons. Why do we ask that? Well, that's the reason we ask that is because if it has electrons, there's one of these that is present, and it's LDF. So we could go ahead and say right now that one of the IMFs it has is LDF. All of them. And the reason is because they have electrons. Okay, are they polar or nonpolar? So looking at this, is this polar or nonpolar? Well, oxygen and oxygen, they have the same electronegativity, so we could say that's nonpolar. H and F, F is definitely more electronegative than hydrogen is, and you could look at the periodic table, but honestly, you probably won't have to. I'm not going to give you a question where you have two different atoms that have the exact same electronegativity. So if the atoms are different and the dipoles don't cancel out, it's going to be polar. So this is polar. This one, it's a bent shape. Remember, in a bent shape, even in a bent shape, those dipoles will not cancel out. So this is a polar molecule. And then we have our tetrahedral shape. There's no lone pairs on the central atom, and all of these atoms on the outside are the same. So this is nonpolar. All right, this one, well, it's the same exact shape as this, so you'd say that it's nonpolar, except you notice that one of the atoms is different than the rest. Okay, that makes it polar, because fluorine has a higher electronegativity than any of the other atoms. All right, so now we can make some progress, okay? If it's nonpolar, and also, does it contain a FH, NH, or OH bond? No, it does not. Does this have an FH, NH, or OH bond? Well, that's fluorine and hydrogen. Yes, it does. Okay. FH, NH, or OH? Well, it's F, but that's with O. F and O, not FH. Okay. I see a CH bond, so anyways, that's no for that one, and it's no for this one. And down here, well, I've got H and F in the same thing, but is there an HF bond? There's not. There's a CF bond, so that's a no. All right, so all we have to do is decide what other types of intermolecular forces we have. We have LDF for every one of them. If it's nonpolar, it's just LDF. You keep moving. If it's polar, then it also has dipole, dipole. Because remember, a dipole is another way of saying it's a polar molecule. So dipole, dipole forces. And because it does have a HF bond, it also has hydrogen bonds. This one's polar, but it doesn't have HF, NF, or HF, HN, or HO bonds. So this is it has dipole, dipole, but it doesn't have the hydrogen bonds. This one's nonpolar. Since it's nonpolar, it's just LDF. This one's polar, but there's no hydrogen bonds, so we're just going to put dipole, dipole. All right, here's our big takeaway. Nonpolar molecules will only have LDF between the molecules, or you could write the full name. London dispersion forces. I would just put LDF most of the time. Okay, polar molecules will have LDF and dipole, dipole forces between the molecules. Polar molecules that contain a HF bond, an HO bond, or an HN bond. I think it's actually normally written, yeah, FH, NH, or OH. It doesn't matter. You could write it either way. But a bond between H and F, H and O, or H and N will also have what we call hydrogen bonds between the molecules, in addition to the other two intermolecular forces, LDF and dipole, dipole. Okay, now you should be ready to do all of the practice problems that we've given to you. If you have any questions, let me or your teacher know.